Today, we'll be discussing linear regression. By way of introduction, the term regression is a historical anomaly. It was coined by Francis Galton in the 19th century to describe a biological phenomenon. The phenomenon was that the height of descendants of tall ancestors tend to regress down towards a normal average. This phenomenon was known as regression towards the mean. It simply means that the average value of y, which is a function of s, that is, it changes with x. So what this one here is just talking about is when we are trying to determine the value of y, which is an outcome variable or dependent variable on x. The value vary, the average it changes with x. That's what it means. So somehow, the word regression is an anomaly. But that was the word just stick to the statistical method. The word regression sounds like go back in some ways. The term has appeared in early writings since the late 13th century and is derived from the Latin word regressus, which means a return. Regressus, so the Latin word regressus means return. It is used in different fields with different meaning, but in any case, it is always referred to as action of regressing. So in philosophy, regression is used to indicate the inverse logical procedure with respect to that of normal apodictics, that is demonstrable or indisputable truth, in which we proceed from general to the particular. Whereas in reality, in regression, we go from the particular to general, from effect to cause, condition to the condition. Let me just quickly explain what I mean by all this grammar here. You know, why they say it's an anomalous is that in the original work, it means that it's moving in the original meaning of regression. Regression means going back. And in that sense, it's trying to look at from what is causing something to what is being caused. Then nowadays, what we use regression to do is we start with the effects. And we now say, okay, what are those things that contribute to this effect? For example, now, we may say, okay, the peak expiratory flow rate for adults or for children. What are those factors? Is the outcome variable? We want to know what are the factors that are responsible, that contribute to this peak expiratory flow rate. Sex, height, many things, age. So many things, many other factors, the presence of disease. So all these factors will contribute to peak expiratory flow rate. So the outcome measure is peak expiratory flow rate, but all these other ones, they are things that contribute. So you are moving from, but first of all, you are trying to say, okay, what are those things that you determine the condition, the peak expiratory flow rate? That's okay. What are those factors that are responsible that contribute to this peak expiratory flow rate? And that is why in your research, you have an outcome measure. That outcome measure, you do your literature review to really know, okay, what are those things that contributed to this outcome measure? So you are starting with the effects. You want to determine what are those factors that contribute to this effect. So it's like you are moving from particular to general. The particular there is one condition. The general, it can be as many factors. That's why when you do your literature review, You do extensive literature review to really know many factors you think may be contributing to this outcome. But at the end of the day, through regression, you'll be able to pinpoint what are those factors that significantly determine or predict the value of this outcome. Now, in statistics, the term regression has an ancient origin and a very special meaning. The man who coined this term was a certain Francis Galton. Was a geneticist. He was a geographer also, he was many things. So you look at the picture of this Galton, you know, from what I have here, you can know some things about his life. Late 18th, Francis Galton influenced by his cousin, Charles Darwin. So Charles Darwin, the popular Charles Darwin, the proposed theory of evolution, was a cousin to Francis Galton. Early 90s, Gregor Mendel genetic work with P realized as important. Now you look at it, after Darwin and Darwin, even Francis Galton, Gregor Mendel, started his own work. In 1920s, quantitative genetic developed. 1950, DNA discovered by Watson and Crick. Early 2000, human genome sequence. Now, Galton was a geneticist. More than that, he was a geographer also. It was, in those days, these scientists dabble into many things. Was a demographer. The man, okay, in 1889, he published an article in which he demonstrated how every characteristic of an individual is inherited by their offspring, but on an average to a lesser degree. So that is, what it means is that it doesn't really mean that everything will be inherited. Of course, it makes sense because a person is combination of, it's formed by the gene from two parents, one mother and father. So there's no way a particular characteristic can purely transmit from the father or from the mother to the offspring, purely, because it has to be a combination of two people. For example, children with all parents are also tall, but on an average, their height will be comparatively less than that of their parents. Even if the two parents were tall, the children of tall parents will be tall, but they will not be as tall as their parents. The same thing, children of short parents will be short, but will not be as short as their own parent, as the parent. So, for example, children with tall parents, okay, I think I've said that. This phenomenon is also graphically described as regression. So, it's described as regression, that is regression towards the mean. So, what it means, there's an average in the population. Since these people, they are extremely tall, they are taller than the average. So when they have the children, the child will try to move back to that average. If some parents are extremely shorter than the average in the population, so the children will be short, but they will be taller in the sense that they will move away. They will not be as short as that. They want to go up to meet the average. That is where they coin the word regression. Regression towards the mean. Since then, this term has lived on to define statistical technique that analyze relationship between two or more variables. In Galton's word, this corresponded to the concept of regression towards mediocrity, and the name of the statistical analysis technique. Regression towards mediocrity. I think we'll soon finish the historical background. The Gatti Universal Regression Law was confirmed by Carl Persson, Gatti student. Carl Persson, last time we discussed correlation, was the one that first of all described correlation. Carl Persson was the one that first of all described correlation from covariance. But actually, the first person to coin the word correlation was actually Galton himself. This Galton we are talking about was the first person to coin the word correlation. But his student, Carl Persson, was the first one to now describe Persson correlation. And that is why the first one to be described is called Persson correlation. It's named after Carl Persson, who was a Galton student. He collected more than 1,000 heights of members of family, that's Galton. He found that average height of the children from the group of short parents was greater than the average height of their father's group. Average height of the children from a group of tall fathers was lower than the average height of their parents. That is, the height of the tall and short children were regressing towards the average height of all people. So please, you start typing, or if you have questions, you can just type it. So when we finish, we'll. So regression is a way of predicting an outcome variable from one predictor variable or several predictor variables. So when you predict an outcome, just like what I said, you move from, so in regression, the concept is about moving from particular to general. You have the outcome. You want to say, okay, what are those things that contributed to the outcome? Know that, and it has formed the basis of thinking in research. Because whenever you have a research question, the research question is always about the outcome variable you want to study. That one, there must be one variable, maybe teenage pregnancy. Think of it, maybe blood pressure, maybe think of anything. That particular thing is the outcome, but you want to know is the research question that is causing problem. Now, you cannot do, for you to remove the problem, you cannot deal directly with that research question. You want to deal with those things that you think may be causing it that you can that are easily amenable. For example, now, we're talking of peak expiratory flow rate. What can you do? It's a biological phenomenon. You cannot open somebody and begin to, there's no way it is written somewhere. I say, oh, see peak expiratory flow rate, how will I adjust it in the body? Or this is the blood pressure, you open it. It's not possible. What you can do now, you look at some modifiable things. Though some are not modifiable, but there are some that are modifiable that you think are the factors. You want to know those factors so that when you are changing, you're able to solve it. Of course, the ones that are not modifiable, you manage them. Like age now is not modifiable. Where age is not modifiable, the aging process may be modifiable. Some of the changes that occur during aging, maybe you can modify them, but age itself, that the number is not modifiable unless somebody just tell, like those of you just tell lie about their age, but it doesn't mean that the age has changed. Sex is not modifiable. Even though some stupid people try to say that they are transgender or whatever, and they try to operate and remove their sex organ and replace with the opposite, is because of the concept of gender. That is a psychological issue. That is so well, this social role. So you will now see that whenever you form your research question, the variable involved is the outcome variable. And you want to know what you now do is to do literature review about many factors that may contribute to that outcome variable. But many people, they get involved in some research because they don't understand research concept. They will have, yes, outcome variable. They will still want to know what the outcome variable can lead to in their research. That is futile this thing, because the problem with that is that if you say, okay, this is my outcome variable, what does it lead to? If you pinpoint something and this is what it leads to, how does it affect it? But you can be sure that that particular variable you're talking about, that your original outcome variable can lead to many things. So picking only one and say, does it lead to this one? It doesn't make sense. If you cannot categorically say that it leads to this, the effect of this your variable on the other variable, unless you also do literature review to involve many other variable, so that you can remove the confounding effect. Can you see that? So you discover that your research is not focused. So if you have one research question per time, you don't go and be looking for what this particular research question can lead to. That one is just will be your justification. Okay, it can be shown that it leads to this, and that is why I want to solve this problem. That one can be your justification, but your data collection cannot do that. What you are now looking for is what are those factors. You now collect data about many factors that will lead to that your outcome variable. And that is why in regression, the outcome variable is one. You now predict it from, you can predict from only one exposure variable or several predictor variables. When you are dealing with only one exposure variable or predictor variable, predicting your outcome, that is simple regression. When you have several, that is multiple regression. Remember, don't be confused here. We are talking about linear regression. We will talk about linear regression. But we have logistic regression. In logistic regression, is this the same thing? You can have one exposure variable, which is simple logistic regression, and several exposure variables which is multiple regression. So now we'll start to cool down to linear regression, even though I've not made mention of, okay, maybe there is logistic or linear regression before, but we are discussing linear regression. But linear regression actually is the origin of the regression, because with all this history, you will see that the example that even are given by Gartin, the person that invented it, that first described it, were continuous variable heights. So something that is number is a continuous variable. It was later that intelligent people, okay, that's okay. What are variables that are not continuous, that are categorical, that you can only have category? How do we predict? How logistic regression. How do we predict rates? That's how Poisson regression. So when it comes to survival, that's why we have cost proportional hazard regression. So your different type of regression that happen are actually offshoot of linear regression. So we can predict any data using the following general equation. Outcome is equal to model plus error. So in that regression, the logic behind it is to predict the outcome from a model you build with the exposure variable or with the predictor variable. And the predictor variable can be one, can be two, can be three, can be many. Of course, because it is quite difficult and it's not even possible to 100% predict, with a model, that is to predict in a 100% way the outcome variable with one exposure or two, even many exposure. Is difficult to 100% predict. There is always a room for error, cannot be exactly the value, and that is where the error comes from. I only give an example. Many times you want to build a house or you want to build a company or church or cathedral or anything, or even if it is a project, bridge or refinery, think of many things, you have a model. The model may be in form of diagram or something smaller version constructed, of that particular thing you want to bring out. The model is not the actual thing you want to build, but it's not the actual structure, but it's a representative. It can be a small version of it. You may not use the same material, something portable, or can even be the diagram, just to show what you want to do. Of course, by the time you see the model, But it's not always, you know that it's not always true that whatever you see in the model, by the time you finish the structure, it will be exactly the same thing. No, it will not be. You see that there will be difference, and that will be the error. Now, we come down to linear regression. The simplest way or description of a relationship between two continuous variables is a straight line. Now, as I've said before, the origin of regression is linear regression. That's the first one to describe. And the variable is continuous, the predictor, the outcome variable. And most of the time also, even when it was first described, with exposure that are continuous also. So let's assume we are starting with outcome that is continuous. Yeah, the exposure also is continuous. So the simplest way you can look at the relationship between two continuous variables is to see that if this one increased by 1 unit, how much will this one will it increase or decrease? If the age of the child increase, will the height of the weight of the child increase or decrease? So in a quantify, so that's what we call linear. So linearity means that something is changing in a linear manner. As this one change, does this one change correspondingly, either in the same direction or in the opposite direction? That is the linear relationship. Okay, so in that situation, the simplest way is using straight line. So this statistic now borrow this because the issue is about building model, as I've said. So in regression, you are building a model, and that building can be diagram, it can be even table, it may be physical structure you are building, but it represents for you to be able to conceptualize what you are trying to do. So you know that, I don't know, let me just let you know that in statistics is about modeling real life situation. Some of these things we are talking about, you see, if there are something that there are things that occur, but how are you able, just like mathematics, of course, as is the branch of mathematics, you try to see the real life situation, you put it in equation, or you put it in a diagram, or using a table to represent it, whichever way, either you use equation or formula, or diagram, or picture, or table, you are representing that life situation on paper or whatever, even in electronic form, and that is what is happening. So the statistic is actually like that. And for this linear regression, it borrows from mathematics equation of a straight line. You remember? So that's what I am showing this slide. How do you represent straight line? That's what it means. There are two characteristics that define straight line. In the equation, you see, straight line, when we talk about a straight line representing two variables now, let's say one with two variables. One is the outcome, one is the exposure. So in the equation, y is the outcome, is the dependent variable. Y x is the independent variable. Y is the dependent, x independent. Now, the two characteristics that define, if you look at the equation now, apart from y and x, you can see m and c. Those are the two characteristics that define that straight line. The straight line that represent the relationship or present the relationship between y and x. The characteristics of the straight line are m and c. And you see the same thing you see in the equation, you see on in the graph. So the m is the slope of the graph. The slope means how slant it is. So if it is very almost steeply slanted, you know that the slope is very high. If it's almost flat, the slope is very low. Of course, if it's horizontal, the slope is 0. So if it's vertical, it's infinity. So now you see the slope. How you define the slope? You define the slope by the change in y. Y we have already said y-axis. The vertical one is the y-axis, which represents the outcome. The horizontal axis is the x, which represents the exposure. So the change in the outcome, which is the y, over change in the exposure. Look at this graph now. You see that for you to calculate the slope, just okay, you draw a point on the from here on this line. You can draw 2 points from here to here. So if you now draw what is the change in the x, it will be horizontal line from here to here. So you draw it from here to here. What of change in y from here to here? That is something from here to here. So change in y over change in x is the slope. If it's very steep, you will see that the more of it will be on the y, the small will be on the x. That's so that when you now divide, you know the numerator is higher than the denominator, it will be, the figure will be high. The flatter it is, the change in y will be small for a very big change in x. That shows that the slope is very small. So slope is 1. Number 2 is the constant, which is intercept. This intercept is where this graph crosses y-axis. The graph also can cross x-axis, but in this situation, what is it? We are interested in where it crosses y. The reason is very simple. The y is the outcome variable. And what it shows that whenever it crosses, when the graph crosses y, it means that the value will be of x will be 0 because at this point, if you are moving along this, it will be 0. But y has a value. This, we are just representing this graph. Actually, the graph, you can continue the line like this. If it continues, okay, let me just get, instead of, let me draw something. The graph can continue, can you see? It can continue like this. So in that situation, if you see, it's not showing me permanent, okay. In that situation, okay, it went off. It's not a permanent. Yeah. Yes. So if you let's say you continue this x-axis, you extend it to the negative side like this, and y-axis you extend this to this one. So you know that this is 0. Anything above y is positive. Everything by above 0 on y vertical axis is positive. Any part of the y that is below 0 is negative y. The same thing, this is 0. Anything to the right of the 0 along the x-axis is positive. Anything to this side is negative. So we are just showing, this one is just showing the particular, because in fact, the graph, if you look at it now, it crosses x-axis also. Because the graph will cross x-axis, it will cross y-axis. But in the equation of a straight line, we are interested in where it crosses y-axis, because that is the outcome variable. And the logic behind it is that at that point where the graph crosses y-axis, x will be 0. Of course, where it crosses x-axis here, y will be 0 also. Whenever it crosses x-axis, y, look at it, the value of y will be 0 also. So we are interested in where it crosses y-axis, because you are predicting y from x. It's not only x. Maybe if it is only one, even if there are 2 or 3 variables that are the predictor, they are not the only one that may be determining y. So for the fact that those variables you are representing in the graph, they have no value at that particular point, or maybe a real change. If their change is 0, doesn't mean that y will not change, or something will not, or y will not have value. That's why you call it, that intercept is value of y when x is equal to 0. Value of the outcome, the dependent variable, when the value of the independent variable is 0, or when there's no value there, the y still has value. Now, one thing I just want you to know here is that those two characteristics, the slope and the intercept, what do? There are 4 scenarios that can happen, which we'll not talk about. Maybe later we'll talk about it. There are 4 scenarios that can happen. I don't think I put it in the slide here. The first scenario that can happen, I think, is with the correlation slide. The first scenario that can happen is you can have positive slope. This one is positive slope because it's slant, it goes up towards the right. But if as you are going towards the right, it goes down, that will be negative slope. So the slope can be positive or negative. Those are 2 possible for slope alone. The intercept, where it crosses y-axis can be positive, it can be negative. Imagine if that line just come like this. It will have crossed y-axis at the negative side, even though the slope is still positive. This graph can be like this. This one can be like this. In this case, if the same intercept is negative slope, the same intercept is positive, the negative slope. But if this one that is like this can be like this also. It can cross y-axis at negatives and the slope will be negative. Can you see? Those are the 4th scenario now. Because you can have positive slope, negative slope. You can have positive intercept, negative intercept. So when you combine the two now, so it can have positive slope, positive intercept, positive slope, negative intercept, negative slope, positive intercept, negative slope, negative intercept. So you can see you have 4 possible scenarios when you combine the intercept and the slope. And what the slope does is just to show you the shape. Does it slant up? Does it slant down? While the intercept show the location of the graph in the geometric space. Of course, when it is positive, it's above 0. When it is negative, it's below 0 value. That's what it means. Let's move further. Okay, let me stop this annotation. Okay. Okay, I think this thing idea, I was even thinking the slide is not here. This I think I just said. Now let me erase this. Clear the hair. So can you see what I just said? Positive slope. That is what we have shown before. Negative slope. But both of them, for both of this graph, you see that the intercept is still positive because it still crosses y-axis above 0 on the positive side. But we have line rising from left to right, positive. Negative slope, line rising from right to left. And then go down, yes, or go down from left to right. Slope is 0. Line is vertical, not defined. So now, what I was saying the other times, what the slope and intercept represent, this is exactly what I was trying to let you see. I even know that it was. Now you can see that this one has positive slope, positive intercept, the first one. The second one, has positive slope, negative intercept. The third one has negative slope, positive intercept. And the last one has negative slope, negative intercept. So while the slope shows the shape of the line, the intercept shows the position of the line in geometric space, or location of the line in geometric space. Now, the equation of a straight line, was now adopted for statistics from mathematics, because we just describe what it is in mathematics. Though it's still the same thing in statistics. The statistics try to change the nomenclature. Instead of writing y is equal to mx plus c, as in mathematics, in statistics, you write like y is equal to bx plus a. So m is b here, and c, which is the intercept in mathematics, is a in statistics. But it's still the same thing. So the b, which is the slope, is referred to as the regression coefficient. Regression coefficient. That is, we already shown is the change in y per unit change in x. You remember further mathematics, dy dx. In calculus, dy means change in y over change in x dx, y dx. So here, the slope just means the regression coefficient, which is change in y per unit change in x. So if x, y is your outcome variable, so for each let's say the outcome variable is blood sugar and blood pressure, and the exposure is salt intake. If for each unit, maybe 1 gram or microgram or 1 gram increase in the intake of salt per day, what effect does it have on blood pressure? By how much does it increase blood pressure? So per unit change in x, that is, in the x, the exposure variable, the independent variable, if it changes by 1 unit, how much of the y will change? That's what it means. That's why you divide y by x, change y by changing x. So that's just it. And we already said that the a is the constant, is the intercept, the value of y when s. So this b is the regression coefficient. Now, the regression equation now. It's the same equation, but try to deodorize it for simple linear regression for multiple. In simple, we have already said y is just only one variable. The x also is only one variable. So instead of writing that the a, which is the intercept constant, you see write it as b also. They'll call it, it doesn't have coefficient, b0. That is, it doesn't have its own coefficient. B0 is the constant, is the intercept. Why? B1 x1. The B1 is the regression coefficient for x1, that variable. If there are more than one variable, in this case, maybe you have 2 variables, 3 or 4. So you still have the intercept, which is B0, while the regression variable will be B1, B2, B3, B4, up to Bn, as many, for each of x1, x2, all those variables. Simple. Of course, when you do it, you may still get your error. Still. So in order to explain it further, so in order to put in a better perspective, look at the model. It's the same thing for linear, simple linear, multiple. So you write it as beta. That b can be written as beta. Beta 0 plus, this is only one variable x, exposure variable. This is the regression coefficient here. Why is the error? This is the error. So this one below is for multiple linear regression. Now, here, actually, what this one shows is showing the change in by predicted output. Change. But I think here it should be, it's better you explain it here. We won't stop because if it's becoming too technical, you have to get it bit by bit. The next lecture we'll try to complete it. Regression model, the same model, if you put it on the graph, the same graph we have looked at. Now, what this model is doing is to represent the straight line, is representing the relationship between X and Y. But of course, when you plot the variable, the exposure, which is X, and outcome, which is Y, the scatter plot, I mean, the graph, what actually comes before this line comes is that where for each person, maybe if you have 300 people, for the first person, where the value, this is the value of X here, this is the value of Y, where they meet is where the dot is. So each dot represents the joint, the meeting point of the horizontal line you draw from the value of Y and X to each dot. So after drawing the line, what you now see is that there's a deviation. You may not get all the value on the line. In that situation, some will be above the line, while some will be below the line. I think this one just show you this is the data point, this is the regression line. I think the next one, if you are to actually draw after plotting it, because the plotting before the line, after plotting it, if we are to draw the line, the best line, there are two options. We can plot maybe physical plotting and give to individual, draw the best line. You see that if we give these two graphs now, that those two scenarios, if you give it to anyone, different people, they cannot draw the same thing. They cannot, the line you're going to draw will not be exactly the same. Because each person is trying to say, where is the middle? Where are we going to draw the line? So now the best line will be the line that reduces the distance from each of the point. And we call the method of least square. The best fit, the best line would be the line of best fit. And the best method to do it is method of least square. The method of least square, what it means is that as you have the line, we have the dots. We want a line that, if we draw it, of course, we know that since all of them are not perfectly on a straight line, we want a situation where this line will be the closer to each of them. And how do we do that? Mathematically. You know, mathematics, you just want to say, okay, do I multiply, do I add? If you look at it, if you draw a line, all those ones above the line, they're above the line. The one below, they are below in value. The distance between the line and each point is the difference between the line and what is predicted by the line and what is the real value. Of that value of Y is this one at the dot. But where the line you draw from it meets the straight line is the predicted value by the model, by the line you draw. So the deviation and the difference is the deviation. For those ones that are above the regression line, the deviation is positive. For those ones below, the deviation is negative. If actually it's the best line, when you add the positive and negative, it will cancel it with zero if you add it. But of course, you will have known from the time we calculate, you want to calculate variance, standard deviation and variance from mean. You know that statisticians don't do that because they know that when you say something is the mean, it's in the middle. So deviation, all those values above the mean or the middle will be positive, all those values below will be negative. When you add them together, it will be zero. So they square it. That's where the squaring comes from. So if you now square the deviation, the positive will remain positive, negative will become positive. So in that situation, there's nothing canceling one another, all of them will be positive. If you add them together, so it will not give you a value, which is called sum of square. We have seen that when we're talking about even and over, talk about ANOVA, where we talk about standard deviation. Now, if you square it, and now it's going to give you sum of square. So if we are to give it to different people to do now, we will likely get different value because we don't draw the same line. So the best line will be the one that when you sum the deviation to give the smallest. That's why they say method of least square. That is, it will give you the least value. In that situation, it's telling you that all the different points are close. That's the best you can do. They are as close to the regression line as possible. Method of least square. So now I think we maybe want to stop here. So after you have drawn that, the next thing is for us to now, okay, calculate the slope. Since you have drawn your line through the method of least square, you can be sure that that is the best line, because the one that gives, that makes sure that each point is as close as possible to the regression line. So you now calculate the slope, now calculate the intercept. You now know where does the line meet, whereas that is the intercept. If you go back and then put it into equation, the initial equation, you know your slope is, remember, okay, let's use the that y is equal to a plus bs. B is the slope, a is the intercept. So if you now bring somebody a value now, or for your, you bring a value somebody, this is the salt intake of that person, X. You feed into the formula. Since you already gotten A and B, you know the intercept, you know the slope, regression equation, and regression coefficient, you'll be able to calculate to Y what the blood pressure will be. Of course, it may not be as accurate, there will be error. How will you know if there's going to be error? If you use a particular data set to plot the line, and you're able to get your B and A, choose one of them. You know, in the data set, you have the Y and X for each person. Choose the X for one person and calculate, choose the X for one person, and now use your P and A to calculate the Y. You will see that it will not be exactly the Y corresponding Y. It's telling you that there's an error. But whichever way, so the error varies. So you're able to predict to a certain extent. So we'll be talking about how do you do that? How do you know after plotting? How do you know how good? Because we know there's error. How do you know how good this line is before you go ahead and be saying that, yes, I'm predicting. You may be predicting what you're predicting may be far from the truth. So we'll be discussing that, how we are able to know to do it. We call it goodness of it, test of goodness of it. What are the tests of goodness of it? To show that this regression line is good enough to predict before you now depend on whatever is giving you. I think we stop here and let's ask questions. So by next tomorrow, go and look at the test of goodness of it. Any question? So it's so clear. If you have question, you can, nobody type any question. I didn't say the chat. If you have question, you can voice out and ask your question.
Good evening, sir.
Go on, no question. Okay.
Somebody is talking.
Okay, who is talking?
Good evening. Good evening, sir.
Good evening.
Yes, you said when
we're not hearing you. Who is talking? Maybe network.
Good evening, sir.
Good evening, Dr. Morige.
Sir, happy New Year, sir.
Okay, same to you.
Okay. You have never disappointed, and it just happened again. Thank you so much, sir.
Thank you. Yeah.
For this lecture, sir.
So it's very clear. Okay, go
very
on.
clear, sir.
Okay, go on.
I want to ask, sir, as the principle changed, this linear regression, simple linear regression, is actually between two continuous variables, the dependent continuous, the independent continuous. Has it changed?
No, if you look at it, what I was saying was that the first description, when the origin of it, for describing it, is to use the dependent continuous, independent continuous. As knowledge increases, you use it to predict continuous variable. The outcome has to be continuous, but the exposure doesn't have to be continuous. That's just it.
In simple linear regression,
Either simple or multiple. What I'm saying, in linear regression, the outcome is continuous. The exposure may not necessarily be continuous. Not all of them will be continuous. Okay. It doesn't have to be continuous. Yeah, that's what I'm saying.
Okay.
Yeah, it can be categorical. So when we get there, the logic behind that you get to know. If you were in the lecture on the correlation, we talk about bilinear, biserial, and point biserial correlation. You can correlate continuous variable with a categorical variable like sex. So you can correlate blood sugar, which is a continuous variable, with sex, which is male or female. All you need to do is to say, okay, male will be 1, female is 0, or female 1, male 0, depending on which way. It depends on the direction you want it to go, especially if the blood sugar is higher in male, in female, you may say female 1, male 0. You get it now, male 0. So in that situation, when you are doing it, you can do regression. So sex may be a predictor in that situation, but you have to create dummy when you are running it. You have to create a dummy to that effect. So in that situation now, the outcome is continuous, but exposure is categorical. Does it make sense now? So in linear regression, is the outcome that needs to be continuous. The exposure can be anything. It can be continuous, it can be categorical.
Okay, sir.
Some people are shouting now. Yeah.
Thank you, sir.
Yes. Somebody has a question. When you find the square deviation of the positive and the negative deviation, what do you do thereafter? I don't understand from that point. What I said was that if for you to go further, if actually that line is a perfect line, as many that is actually in the equidistant from all of them, as many that are above would be below. At the end of the day, the one that are above, the deviation will be positive. The one that are below, the deviation will be negative. At the end of the day, if you add positive, what do you do with it? No, you cannot go further. It becomes, you add it together, it will be 0. So that is why they square it. When you square it, it gives you a value. The what we are is for comparison anyway. So what we are saying is that when you give you a value, you want to be sure that that is the least it can give. That is, if we have to draw many lines, if we do it like that, the one that gives us the smallest when we square the division and add everything together, the one that is the smallest, that is the best line, because that's the one that is closest to all of them. That's what it means. So that's why it's called, that method is method of least square. That is the least. When you square the deviation, you add them together, is the least, it gives you the least value. That is the usefulness of the method. I don't know if it's clear. That depends on the question, because you say, like, what do you do with it? It's just for you to know that that is the best line. Another one. Somebody asks, is it always necessary to put the equation of the regression in the graph in one statistic? Well, it's not necessary. Are we together, please? Where it's not necessary in the sense that if it is for only one, most of the time you are doing multiple regression. If it is only one you are doing, Yeah, it is. You can do that. But most of the software cannot, if when you are doing multiple, you need software that give you multi-dimensional what do I call it, 3D software, so that you can actually see the relationship very well. It's not always necessary. What usually people just do is that when you can do this, when you are dealing with correlation, before you proceed to regression, you can do the scattergram. When you do the scattergram, you make sure, since you want to produce, like the correlation, if you want to do the correlation, we say correlation, there's no why, no expect. Of course, when you begin to know that you are going to regression, you have to make your outcome variable to be y and your exposure variable to be s. So it's not necessary for you to plot the graph. Okay, any other one? Okay, I think there's no other question. There's no other question. I think we can pause here.